Hello everyone, this is Sankararao Varri, a research scholar from National Institute of Technology, Warangal, India, and Institute for Development and Research in Banking Technology, Hyderabad, India. I am the corresponding author of the paper Key-Escrow Free Attribute-Based Multi-Keyword Search with Dynamic Policy Update in Cloud Computing, and this paper is published in CCGrid 2020. Let me start my presentation with the introduction. Because cloud is providing many benefits, huge amount of data is outsourced into the cloud, and this outsourced data may have some sensitive information. Here, sensitive information is nothing but any information which is private to particular individual is a sensitive information. And what will happen if we outsource sensitive information into the cloud? So because the cloud service provider may be interested, or he may be curious to know what is the user's data, or there may be a possibility of internal or external attacks. With all this, we can say that the privacy of the sensitive information is reduced. So to achieve privacy of outsourced data, we can encrypt the one possible option is we can encrypt the outsourced data before outsourcing it. And with this encryption of data, we can achieve privacy, but the search functionality of this encrypted data is not there. Means if you want to perform a search over encrypted data, you have to download the entire data and decrypt it, perform a search, again encrypt it, and outsource it. This includes huge amount of communication and computation cost. So that is not feasible. So searchable encryption is a solution where this searchable encryption allows users to perform search over encrypted data itself. There are many searchable encryption schemes. There are many searchable encryption schemes like symmetric searchable encryption and public key searchable encryption. But these schemes are having disadvantages like existence of secure channel, complex key management, and user access control. Okay. With this, attribute-based searchable encryption schemes achieves fine-grained access control. Here, access control is nothing but for any particular given file, only set of users are allowed to access that particular file. The remaining of the users are not allowed to access that particular file because we are controlling the access of the particular file. So that is access control. So this attribute-based searchable encryption schemes achieves this access control along with keyword search over encrypted data. Okay. With this introduction, we performed a literature survey over these attribute-based searchable encryption schemes, and there are two types of ABSC schemes, that is key policy ABSC, that is KP-ABSC, and ciphertext policy ABSC, that is CP-ABSC. In key policy ABSC, the secret key is created with access policy, and ciphertext is created based on user attributes. In CP-ABSC, the secret key is made up of user attributes, and ciphertext is made up of access policy. And we thought that the CP-ABSC is suitable for our approach, and we adopted the CP-ABSC architecture. And with this, we also performed the functional comparison of our scheme with some recent schemes. The functionalities are like multi-keyword search, fine-grained access control, Key-Escrow free, and dynamic policy update. And we say that all these four functionalities are included in our scheme. Then let me introduce my proposed method. It is having 5 participants, namely third-party authority TA, attribute authority AA, data owner DO, data user DU, and cloud server CS. Here we are using 2 authorities TA and AA to generate public keys and secret keys because none of the authority should know the complete secret key of the data user. So by this, we are eliminating the key escrow problem. And there is a secret sharing between TA and AA. This secret sharing is based on secure two-party computation protocol. Okay, and the role of data owner is to generate the ciphertext as well as index. This ciphertext is generated based on the access policy. Means this ciphertext includes the access policy. And index is based on the entire keywords from the files, means all the keywords from the files are extracted and created as an index. So this as a ciphertext and index are separately outsourced into the cloud server. And whenever DU wants to perform a search, means when he want a particular document from the cloud, he issues a trapdoor. This trapdoor is made up of the secret key, and this trapdoor is generated to the cloud server. Then cloud server performs search between this encrypted index and trapdoor. And if there is any match, means if there is any match between the keywords in the trapdoor and the keywords in the index, then the particular documents will be retrieved. And obviously, after retrieving the results, the data owner can able to perform decryption. So this is our proposed method. And with this, I will introduce the list of algorithms which we have used in our particular scheme. Okay. Here, first of all, setup.pa. This algorithm is run by trusted authority, that is third-party authority, and it takes security parameter lambda and universal attribute set as an input and outputs public key 1 and master secret key 1. Setup.aa, this algorithm is run by attribute authority. It takes security parameter lambda as an input and outputs public key 2 and master secret key 2. Then key generation.aa, this algorithm is generated by, this algorithm is run by this AA, and it takes master secret key 1 and ID of the user and master secret key 2 as an input and outputs secret key 2. Here, this master secret key 1 is associated with TA, but we are using this MSK1 in keygen of AA. How it is possible means we are not directly using this MSK1 in AA, keygen.AA. We are giving this master secret key 1 and master secret key 2 to secure two-party computation protocol. This protocol generates a secret value. That secret value is given to keygen.AA. Okay. Based on that secret value, it generates secret key 2. Then keygen.ta. This algorithm is run by third-party authority. It takes public key 1, master secret key 1, and user attribute set yes as an input and outputs secret key 1. Then keyword encryption algorithm. This algorithm is run by data owner. It takes public key and keyword set. This keyword set is nothing but the keyword dictionary, entire keywords of file collection as an input and outputs encrypted index I. Then the document encryption algorithm. This algorithm is run by data owner. It takes a file, public key, and access policy M, psi as an input and outputs the ciphertext. This trapdoor algorithm is run by data user. It takes secret key and the user interested keywords W as an input and outputs the trapdoor. Then search algorithm. This algorithm is run by cloud server and it takes the encrypted index I and the trapdoor TD as an input and outputs whether there is a match or not. If there is a match between the keywords in the trapdoor and the keywords in the index, then it returns 1. Otherwise, it returns 0. Then decryption algorithm, it is obviously run by data user. It takes secret key and ciphertext results, which are from the cloud server as an input and outputs the plain text form of the ciphertext. Then update keygen. This algorithm is run by data owner. This algorithm is run when there is a update in this policy. The dynamic policy. When we are updating the policy, this algorithm executes. It takes public key and previous encryption information of the file and the new access policy M, psi prime as an input and outputs the update key for the file. Okay. So then ciphertext update. This update key is given as an input to the ciphertext update algorithm and it generates the updated ciphertext as an output. Obviously, this algorithm is run by cloud server. With these all algorithms, okay, the security assumption of our scheme is based on decisional bilinear Diffie-Hellman assumption. All our algorithms are reduced to this particular assumption. Not only algorithms, all our scheme, the entire scheme of our proposed scheme is reduced to this assumption. This assumption says that given a true oracle mapping of g comma g power abc and a random oracle z, which is from a multiplicative group of z with prime order p, and we say that there is no probabilistic polynomial time algorithm which can differentiate between this true oracle and random oracle with a polynomial time. Okay, so if this assumption holds, the security of our scheme is strong. Okay. Then we evaluated the performance of our scheme with Windows Mission, and we used Python 2.1 as a programming language, and we have used Charm Crypto library for all cryptographic primitive operations. Okay. And this graphs tells that our scheme is efficient. In this figure A tells the computation cost of setup algorithm, B for computation cost of key generation algorithm, C for index generation algorithm, D for trapdoor generation algorithm, and E for search algorithm. And we say we also compared our scheme with the recent schemes, and we say that our scheme is efficient. And this is computation cost for when we are updating the policy. And there are three types of policy update operations are there. In type 1, all the attributes in the new policy are already existed in the old policy. In type 2, some attributes in the new policy are existed in the old policy. In type 3, all the attributes in the new policy are not existed in the old policy. With all these three types, we performed the computation cost for this policy update, and it is shown in this graph. Okay. Then we conclude our paper we proposed Key-Escrow free attribute based multi-keyword search with the dynamic policy update in cloud computing, and we say that our scheme is Key-Escrow free, and it also supports dynamic policy update, means without downloading the entire policy into the physical disposal, we are updating in the cloud itself. So it reduces the communication and computation cost also. And this work is published in CCGrid 2020. And these are some of the references we have used. Thank you. If you have any queries, you can mail me to this mail. Thank you.